Content-Aware Resizing is an image processing method that allows images to be reshaped without too much loss or distortion of important visual content. But why does this matter? In modern society, digital images are everywhere. Every day, upwards of 300 million pictures are posted on Facebook. Globally, we're expected to take over 1 trillion photos in 2016. But not only has the number of images increased, but also the number of contexts in which we see these images. We see photos formatted for social media on Facebook, Instagram, or Twitter, for news media on and offline, as backgrounds for websites and apps, meant for desktop PCs, tablets, and phones of all sizes and aspect ratios. Because there are so many possibilities as to how an image might need to be presented, the ability to resize and reshape images is hugely important. Let's look at an example you might see in your everyday life. A Facebook cover photo is exactly 851 pixels wide by 315 pixels high. Let's say you want to upload a larger photo. How can you fit an image to this size? Well, the two most common strategies are scaling and cropping. Facebook actually uses both when fitting a larger image to their cover photo template. First, the image is uniformly scaled so as to fit the width of the frame without changing the aspect ratio of the original image. Then, the user is able to slide the image up or down, effectively choosing which area of the image to crop out. In most cases, this uniform scaling and vertically constrained cropping works well. But what happens if you have content that's pretty widely spaced out in the vertical direction? Facebook's built-in strategy might make you crop out some areas of the image you'd prefer to keep. And even if you were to scale the image prior to uploading, any non-uniform scaling would distort the image, and uniform scaling to the point of fitting the vertical content might require pillar boxing. Neither of these are very attractive options. So you might be thinking, there's a lot of uninteresting content over here, and there's a lot of uninteresting content up here. If only we could perform some kind of content-aware resizing, such that only these uninteresting areas were removed, so that the original content could fit in our new vertical constraint. Well, good news, we can. If you wanted to implement some content-aware resizing method, first, you would need some measure of where the important areas of the image are. And second, you would need to reduce the size of the unimportant areas, preferably without disrupting the visual continuity of the image. To find the important areas of the image, the simplest strategy might be to just ask the user where the important areas are. The information from the user could then be converted to a binary map, such as the one you see here, where black areas are unimportant and can be removed or reduced, and white areas are important and should be preserved. This might be fine for resizing an image or two, but if you were to use this technique many times, it would soon become very labor-intensive. So how do we find these areas automatically? Well, in most images, the important areas aren't in uniform regions, they're near edges. So if we find the edges, that should give us a fairly good idea of what areas we should avoid removing. To do so, we can approximate the horizontal and vertical gradients of the image by applying a Sobel filter. Taking the vector magnitude of these horizontal and vertical components yields an edge map. This map is similar to the one before, where dark areas are less important than light, but now instead of being purely binary, these values are weighted based on edge strength. We can think of this as an approximation of the energy of the image, where the most important areas have the highest energy. So now that we know where the important areas are, we want to remove the least important areas until our image is the target size. We could just sum up the values in our edge map by row and remove the least interesting rows. But this could introduce discontinuity in our image, especially if the least interesting rows are right beside each other, as they likely are. Instead, we can define a seam as being a 1 pixel wide connected path from one edge of the image to the other. By removing seams that follow the least interesting paths, we avoid disrupting edges, therefore preserving visual continuity. To find these least interesting or lowest energy seams, we first choose a pixel at one end of the image. We then move 1 pixel in the direction of the other edge, choosing the path of the lowest energy. Repeating this for the length of the image gives us our seam. The average energy of the seam can be represented by the sum of the energies of every pixel in the seam divided by the total number of pixels. If we find seams for every pixel along an edge, the seam with the lowest average energy is probably the best candidate for removal, as it poses the lowest threat of disrupting the image's visual continuity. Since each seam is only 1 pixel wide, removing a horizontal seam results in an image exactly 1 pixel shorter, and removing a vertical seam results in an image exactly 1 pixel skinnier. At this point, the seams can be recalculated and the next lowest energy seam removed, and the next, and the next, and the next, until the image has reached the target size. Here you can see the process in action. Notice how the seams chosen for removal are primarily located in those uninteresting areas we designated before. This not only preserves visual continuity, but also visual accuracy of the content we hope to preserve. The final image, then, contains most of the important content without introducing distortion or discontinuity. If we compare this to the original image, we see that we've captured all the important content as the pier and the surf look relatively unchanged. Comparing this to a vertically constrained scaling operation reinforces this point, as the scaled image is visibly distorted, with the pier and surf being squished to fit the frame. So using content-aware resizing, we were able to fit an image into a smaller constrained area with better data retention and accuracy than our other two methods of cropping and scaling. We can also grow images in a similar manner. To grow images, we calculate the seams just the same as before, but instead of removing a seam, we duplicate it. This results in an image exactly 1 pixel wider in the case of a vertical seam, or 1 pixel taller in the case of a horizontal seam. To repeat this process, we must exclude the seam from our calculations, so that we don't end up adding the same seam over and over again. We can accomplish this by simply setting the values in our energy map of every pixel in the seam to their highest possible values. This way, every time the lowest energy seam is recalculated, it'll be a different seam. This is how the process looks. This image is actually being shrunk in the vertical direction, while being expanded in the horizontal. This is possible because our total seam energies are averages over the length of the seam, enabling us to directly compare the energies of seams in different directions, and remove or add the overall lowest energy seam. When shrinking, we take care to use an independently calculated energy map, such that the adjustments we make to prevent duplicating a seam in the other direction don't impact performance. With this process, we were able to fit a tall, skinny image into a square form factor, again preserving the content and visual continuity of the original image. This is all well and good, but what happens when our edge image isn't the best indicator of importance? Take this image, for example. The houses in the background might have a lot of edges, but the area I'm most interested in is the Mustang. If I try to resize this to, say, a 1280 by 720 wallpaper, our current method is going to perform an unwanted conversion, from Great American Muscle to Ultra Lowrider. So how do we fix this? Well, there's a simple solution, and that's to bring back the user from before. If I generate a mask over the image where white regions are the ones I definitely want to preserve, and gray regions I don't care about so much, I can apply this mask to the energy image, like so. This will cause the lowest energy seams to happen outside of the masked area, hopefully preserving the most important content. In this case, this strategy works fairly well. There's a little bit of discontinuity along the edge of the mask, particularly in the wheel of the black Acura in the parking line. But for the most part, the important area of our image is preserved. So we've seen content-aware resizing increase and decrease the size of images. But that's not all it can do. We can also use content-aware resizing to target and remove areas of images we're not too fond of. Let's use this image of a bridge as an example. Say you wanted to use this photo as a banner for your website. You might want a short but still long image. Well, we've shown how to effectively do this with content-aware resizing. But what if you really didn't want to change any of the sky, and you really weren't fond of that piece of driftwood? Well, like before, we can generate a mask, where the sky is preserved as the white area, and the rest of the image is gray. But now, if we set the area with the driftwood to black, we can remove those edges from our energy image, lowering the energy of seams that travel through that area. This will greatly increase the likelihood of this area being reduced as seams are removed. Here you can see that seams traveling through that area are effectively prioritized, and in the resulting image, the size of the driftwood is greatly reduced. So while it's not a foolproof method, refinement of the energy function or the seam detection process used could further improve performance. And in any case, its performance in constrained resizing and potential for application to more complex tasks, such as seamless feature removal, make content-aware resizing a very powerful tool.